Alright, so hello everyone, welcome to the development kit tutorial video for this year's Argonauts 2025 challenge. My name is Dominik Bersch and I am a PhD student at the CVAI lab with Professor Dr. Gemma Reuk, and I'm also one of the organizers of this year's competition. And in this video I will show you our development kit that you can use to familiarize yourself with the data and to see how to make a test submission for our submission platform, which is hosted by CoderBench this year. And to get some more information about this year's competition, make sure to check out our introductory video. We also have another video about the CoderBench platform for information about the submission process. I will also link both videos in the comment section down below. Okay, so what will you learn today? There are four main sections to this tutorial. First, familiarize yourself with the challenge data. And here we prepared some code that helps you to understand with what kind of data we are dealing with, just to understand the stimuli and the fMRI data. Then learn to extract the stimulus features used to train and validate an fMRI encoding model. Then a section to train and validate an fMRI encoding model. And finally, prepare and format fMRI predictions from an encoding model for challenge submission. And this section will also show you the correct format the submission should be in for the CoderBench platform. You will also be able to execute these sections separately. So that means even though you learn how to extract features in section 2, which will be needed in section 3 to train the encoding model, we will provide all of the pre-computed data, because this way you will have the free choice of deciding which section you want to look at, and you don't have to create the features for the entirety of all seasons, which would be very time consuming. And then you will have some additional information here which you can read through. And also you can run this entire notebook on Google Colab, or you can download it to run locally. For that you can just click here on File, then Download, and then download the IPy notebook. Okay, so at the beginning of this section you will have to decide whether you are executing this notebook on Colab or on Jupyter, because depending on your selection, different settings will apply during the tutorial. Also, you can select the device you are working with. So CUDA is GPU enabled and will make certain tasks faster. It could be that you might have to reconnect your instance for the GPU to work, so just better do this now instead of being surprised later that the GPU is disabled in the session, because then you will have to restart everything. For that you can just click on runtime here and then check if you are GPU connected. Then you can install all the necessary libraries here. For Google Colab, just execute this cell, and for Jupyter, you will have to install these libraries here. And after the installation is done, you can just import all of them and therefore check if everything has been installed correctly. Alright, so this is about that, and now we want to download the challenge data. And to do that, you first have to fill out this form here and accept the terms and conditions. And this will lead you to the Google Drive folder, which I would encourage you to mount to your own drive. And to do that, you can just right click on the name here. And then you can click on Organize and then add shortcut. And then here under all locations, you can add it to your drive. So now if I go to my drive, you can see here that I have a link to that folder. And this basically ensures that you can reach it without taking away space, and also makes it easier for Colab to reach it, which we can see here. So if we go to Drive, you have this folder, My Drive, where we also have this folder located. And you can already see the path here in the root data directory. If you do not want to mount your data like I did, you will have to adapt your root data directory to whatever location you saved your data to. And if you're on Jupyter, you will just have to download the data and place it somewhere you like, but make sure to just update this root data directory. Okay, so with the downloaded data, you will find 3 folders. This first one here will contain 2 further subfolders, one fMRI and one stimuli. And the stimuli folder will contain the multimodal stimuli and the transcript files, which basically contain tables with the spoken words and their onsets, which I will show you in a second. And the fMRI folder contains the subject-wise brain recordings to the stimuli, along with the brain atlas, which is important to visualize the brain data onto a brain plot. These I will show you in the first section. Stimulus features will contain raw and PCA downsampled visual, audio, and language features. These are pre-computed, which you will need for section 3. These are mainly provided for the purpose of this tutorial. How to create them I will show you in section 2. And trained encoding models, this folder contains very simple trained encoding models using all the stimuli features. This is also for the purpose of this tutorial, and how to train a model I will show you in section 3, because this will be used in section 4 for the final submission demonstration. Okay, so let's start with section 1. Familiarize yourself with the challenge data. Here we have a nice figure explaining the different phases, but for a thorough explanation, please refer to the challenge video in the comment section. But in short, for the model building phase, the idea is to train and test encoding models using the fMRI responses to season 1 to 6 of the TV show Friends and to the movie 10 dataset. And the challenge will be to predict the fMRI responses to season 7 of Friends. But for the purpose of this notebook, we will train the model on season 1 to 5 and test on season 6, since season 7 has to remain withheld for the competition. Alright, so what does our multimodal stimuli look like? Since it's a video, we of course have video and audio stimuli, but we also have a transcript of all the movie data, which means we also have the language modality. The movies will be in the MKV format and the transcript in the TSV format. And you will find the stimuli data for Friends season 1 to 7 in the stimuli Friends folder and the movie 10 data in the movie 10 folder. Okay, so now let us execute this function. It basically loads the first episode of Friends and lets us know its properties. And if you wait for a second, we can see that we have about 30 frames per second. The video resolution is 720 by 480 and the audio sample rate is 44,100 Hertz. And we also have a video clip here of the first 20 seconds. The beginning is black, by the way, because of the intro. And yeah, you can just take a look. But what about the transcript files? So these files you can find in the transcript folder in the stimuli folder. And to analyze them, we again have a function here that displays the first 20 rows of the transcript of the first episode, which we can just execute here. Okay. So what do we see here? These transcripts consist of the following columns. We have text per TR, and this basically the sentence that was spoken within a chunk of interest. What is a chunk of interest? So the repetition time of the fMRI recording was 1.49 seconds, and the movie was therefore also separated into chunks of 1.49 seconds in order to be able to be aligned to align the stimuli to the fMRI data. So each row is basically 1.49 seconds of the movie, and this column will show you what has been said in that chunk. Words per TR is just a list of words. Onsets per TR, this is the starting time for each spoken word. And durations per TR is the duration of each spoken word. And you can see at the beginning we have nothing because it was just black screen, and then the words start to appear. Okay, but let's take a look at what transcript and stimuli look like when we align them. And for that, we have prepared a cell that loads the transcript and the stimuli. It's a lot of code and it's just for display, so don't bother too much about it. But what happens when we execute it is that it lets us select any row from the transcript, and then the number of this row times 1.49 is being displayed as a short video. So let's select a hump and a hairpiece, and then you can see the alignment of these 1.49 seconds and the transcript and the stimuli. But yeah, press play to watch the video. I'm not sure if this is recording the sound right now, but there is sound to it. Also, you will notice that in some chunks the words might be cut off, and this is because, again, the fMRI recording was not word by word, but by these 1.49 seconds, which may result that the word is cut off in the middle of being said. Okay, but talking about fMRI data, what does our fMRI data look like? So first of all, you will find the fMRI data, as expected, in the fMRI folder, which will contain subfolders for each subject, being 1, 2, 3, and 5. So we did not include the data for subject 4, so keep that in mind. In the func folder of each subject, you will find the H5 files that will contain the whole brain responses to season 1 to 6 of Friends and to the movie 10 data. The data is also normalized according to the MNI spatial template. It's processed as a time series, which signal was then assigned to 1000 parcels at the end. If you need more information on that, feel free to check out these links here. So each dataset will be basically a 2D array of the shape number of samples times 1000 parcels. Some things to note: most, but not all Friends episodes were presented according to the series order, so sometimes episodes might be scattered across recording sessions. And with subject 2 and 5, we are missing some data, so keep that in mind. Along with the fMRI files, you will also find atlas files, which are files which we use to map the brain responses onto a plot into a 3D brain volume space, but more on that in a second. And this right here will be very important for your submission. It will make more sense in section 4, but as you saw, each set of fMRI responses comes in the shape of number of samples times features, and the number of samples is different for each episode or movie because one sample is 1 TR split of 1.49 seconds, and each episode has a different length, of course. And at the end, you need to predict season 7, and for that you will need to align the features in the same way the fMRI is being recorded. And for training, we can just use the sample number by looking at the data, but you will not have the data for season 7. And this is why we provide a list with all these sample numbers so that you can properly align them, because it's also important that your prediction and the actual brain responses have the same shape. Yeah. Okay, but now let's look at the fMRI data. So this code here again is just for display again, so don't bother too much about it. It will just basically load up the H5 file of your subject of choice and the dataset of choice and displays the data. So if we do subject 1 and the dataset of friends, we will see that we have multiple datasets in this file with the shape of number of samples times 1000 parcels. Again, one sample is a time interval of 1.49 seconds. So depending on the movie end, the samples will change, but the parcels will not. And this is again why you will need the number of samples for season 7 to properly align them. But again, more on that on section 4. And we also have the same for the movie dataset. As you can see here, the movie is also separated into different runs. Okay, so now we know what our stimuli looks like, and we know what our fMRI data looks like. How do we best align them? And this will be rather straightforward because the language transcript is in 1.49 second chunks, so is the fMRI data. So that means the sample 10 in the transcript will align with sample 10 in the fMRI data. And for movie 10 it's the same principle, but you will just have to divide the movie yourself into these chunks. We have some important notes here about the fMRI data which you should carefully read. This part here talks about that the fMRI detects the changes in blood oxygenation in response to the activity in the brain. So that means if there's activity in a region, blood has to flow there, and this is then measured. But there is a delay from the input and the hemodynamic response function, or the HRF, of like 5.6 seconds. So you have to regard that it needs time for the blood oxygen changes to propagate and for the fMRI to capture it. And that's why in our visualization function down below, we introduce the HRF delay parameter, where we introduce a delay between the stimulus chunks and the fMRI samples for a better correspondence between the input and the brain response. So with an HRF delay of 3, if the stimulus chunk of interest is 17, we will then align it with the fMRI sample of 20 because of this time difference with the blood oxygen changes. All right. So below we have two code cells. One is for plotting the fMRI on the brain and the other one for displaying it. The first function basically loads up the atlas data from the atlas path using the NI Babel library. And then we load up the fMRI H5 file. And this function also takes in the chunk index for the chunk of the stimuli as a parameter, which we alternate depending on the HRF delay. Then we take the updated sample from the fMRI data, and then we will initiate an empty array as the atlas file, on which we will then map our fMRI data, and then we can plot it using the class brain functionality. And the function below is again just to display everything nicely. Here we combine the logic from above, where we already aligned transcript to stimuli, but just added our fMRI logic. And in this cell here, we can use the slider to adapt the HRF delay. Again, the value will add to the selected chunk. We will use again season 1, episode 1 of Friends, but now we will also display the fMRI responses to the scene. All right. So this is basically the data we are working with. And as you can see here down below, a nice class brain plot with the fMRI activity to the scene. I would also encourage you to look at other scenes as well to see how the brain reacts differently to, for example, chalk. And here you can see how the brain reacts to Phoebe saying chalk. Okay, so now we understand what our stimuli looks like. That means it's time to extract the features from them. This section here will have three parts. One where you will learn how to extract visual features, then audio features, and finally the language features. And at the end I will also show you how to apply PCA to reduce the dimensionality of these features. And after extracting those features, we will use them in section 3 to train an encoding model to predict the fMRI responses. So let us start with the visual feature extraction. Okay, so here we will extract visual features from the MKV movie files using the slow R50 model. This is a convolutional neural network pre-trained on action recognition on videos, so a very good fit. And we are going to extract mid-level features of this model when we show it to the inputs. So in the first cell, we basically define how we want to transform the frames. This is just how slow R50 requires it to pre-process the frames we deliver to the model. And in the next cell, we are loading the vision model. We load it from TorchHub, and we will also select that we want to extract model layer blocks5 pooling. This is just an example. You can feel free to use any model in any layer. And then we also define the feature extractor instance, which is from the Torch Vision library, and just automates the extraction process. And then this function returns the extractor and the model layer we chose for this example. As you can see, this code will also immediately download the model. And then we have the big feature extraction function. So what happens here? So this function is triggered in the cell below, where we define the episode path. Again, we are using episode 1 of season 1, the TR value for splitting into chunks, and where we want to save the features. These parameters, along with the feature extractor and the transforms function, we put into this big function. Alright, so this function will then load the video clip and then create all the time chunks that we have with the repetition time of 1.49 seconds. Then we will create a temp folder there because we will save these movie chunks temporarily. Why are we doing that? Because we want to have one feature per feature sample. And we have one sample per TR, so we also want to have one model representation per sample. And then we will loop over all these start times and first create a subclip and write this video file of the first chunk into the temp folder, and then we will turn it into frames. But because these frames don't have the format that we need to apply the transforms, we have to transpose them, turn them into a NumPy array from Torch, and then we can transform these input frames. And then with Torch NoGrad, we will use the feature extractor to extract the features to the frames. And this will return the intermediate features, which we will add to our list. And this we will do for each time chunk and return it at the end. So we have at the end one feature per chunk. This process takes some time, which means we will have to wait for a second for it to finish. Okay, so now that it's done, we can print out the shape, and we'll see that it's a shape of 591 times 8192. 591 are the chunks which align to the fMRI samples, and 8192 is the feature dimension of blocks5 pooling layer. And that's basically it. Now we have one model representation of the stimulus for each video chunk, or in other words, for each fMRI sample. Okay. So now let's move on to the audio extraction. Again, for the challenge you can do it any way you want, but for the sake of this tutorial, we will use the mel frequency cepstral coefficients, or the MFCC. If you don't know what it is, check out the link, but in short it's basically, it turns the signal into frequency using Fourier transform, and then maps these frequencies onto the mel scale, and then at the end returns a set of coefficients which represent the audio key features in a compact way. So here again we have this big extraction function, which is triggered by the cell below. Again, we will enter the movie path, the TR. SR is the audio sampling rate, which we will choose. We chose this value because this is commonly used due to the human hearing range. And this all we will feed into the function above. So what does this function do? Just as before, we will load the clip, select the chunk times, create a temp directory, and then iterate through all the start times. Then again, we will create the subclip, but this time we will not save the video, but the audio file. We are creating the subclips here because we want to have only one feature per TR. And then we will use the LibRosa library to load and deal with the created audio file of the current chunk and then apply the MFCC using the browser library. We will take the mean as well because MFCC is computed for short overlapping windows, and taking the mean basically collapses the time dimension. This data we will then append at the end, and we should again end up with one audio feature per sample. So this might take some time again. Okay, so let's see what we have down here. We can see again 591 in the sample dimension, but 20 in the feature dimension. And this is because that's the feature dimension that the audio gave us. And you can also see here how the data looks like for the first 5 movie chunks. Okay, so now we will finally check out the language feature extraction. And here we will not use the movie files, but the transcript files, which are already separated across TRs and have the words listed, which we can easily feed into a large language model. And for this case, we will use the BERT base uncased. This is a BERT transformer which has been pre-trained on a large corpus of English data with self-supervision. And we will use its features for the language modality. So, similar to the vision model, we will first load the language model, and for that we have to load the model itself and the tokenizer that will put the words into the model appropriate tokens. And this one is of course different for each model. And this might take some time to load again. And now, again, a big extraction function, which is again triggered by the function below. Here we define the path to the TSV file of the first episode. Then we will also define the number of used tokens and the kept tokens of the last hidden state. Okay, so what are those? To understand this, we have to first understand that the model will return 2 outputs, the pooler output and the last hidden state. The pooler output is basically a single vector summarizing the entire input that you gave the model. And the last hidden state is a detailed embedding for every token in the input sequence. So if we enter a sentence with 20 words, we will have one feature representation for each word, or whatever the words has been separated into tokens, while the pooler output summarizes the entire input into one vector. And now we also have to think about what we feed into the model, because meaning of words and the sentence only builds up over multiple words. So if we only use the words from one chunk, it might just be something like hump in a hairpiece, which will not give us a good representation of the meaning. And this is why with number used token, we determine the number of tokens that are being fed into the BERT model per feature sample. So this also includes the tokens from the current chunk and potentially from the chunks before, so that we have more words that can create meaning. And this means we'll have many tokens that are being processed in the model, which are summarized in the pooler output, so that's fine. But the last hidden state, there we have one embedding for each token, which might be too much to process for our next steps. And this is why we limit the number for extraction with kept tokens last hidden states, which will, in this case, just return the embeddings for the last 10 tokens that we fed to the model and not all of the tokens that we gave the model. Okay, I hope this was understandable. So let's go back to the big function. Okay, so here at first we will read the TSV file into a pandas data frame. Then we will add a column isNA where we label the rows that have no spoken text. And then we initiate empty lists where we save our tokens and outputs. Then we will loop over the rows of the data frames, or in other words, the chunks. And of course, we only want to use the chunks where words are spoken. So we first exclude the isNA rows. And then we use the tokenizer to tokenize the text from the chunk. And then we also remove the punctuations from the text and append it to our tokens list. Then, as long as tokens are available, we will select the last number of used tokens that we want to use as decided by the parameter, and then convert them into numerical IDs as required by the model. Then we will add the CLS token, which is 101, and the SCP token, which is 102, to the tokens to mark the beginning and the end of our sequence. This we have to do because we have a different range every time, and that's how we best tell the model what's the beginning and what's the end. Then we turn it into a PyTorch tensor at the batch dimension, and then our tokens are ready to be fed into the model. So with Torch Node-RED, we enter the tokens that we have and only store the pooler output, which again is a single vector summarizing the entire input. And here, if we didn't have tokens here, just append nones for this chunk. And then we basically do the same again, but this time extract the last hidden state, which was the detailed embedding for every token. And as mentioned before, we only want to keep the last 10 tokens, which we ensure here with slicing. And yeah, that's basically it. Okay, so how does our data look like? The pooler output again has 591 chunks and a feature dimension of 768. The last hidden state is similar, just with the extra dimension of 10, which is one feature vector for all the last 10 tokens. But that's all on feature extraction. But now you may want to reduce the feature dimension since they might be quite heavy. And for this, PCA might be a good method, but feel free to use whatever you want, if anything. PCA will basically remove redundant or uninformative dimensions, after which the feature dimension will decrease in size while still retaining most of the information. That means it will drastically reduce the computational cost when we train the encoding models. So how do we do that? Okay, so the first cell basically loads the stimulus features that we entered. The data has to be in the format samples times features, which is given, but not with the language feature, because here we have to basically collapse the per token dimension with the last hidden state, and then append the last hidden state data to the pooler data into one array of the shape stimuli times features. So we basically remove the 10 dimension. And then these loaded features will land in this function, which will first of all replace the none values with 0, because we had some chunks in the beginning with no text, for example, or in some other parts. And then we z-score the features using the standard scalar. We do this because PCA needs the data to be centered and scaled. And this scaled data will go into the PCA function along with the number of principal components we want to reduce it to. And for that, we can just use the PCA function by sklearn and specify the number of components we want to maintain, or in other words, how big the feature dimension is supposed to end up as. And that's it. So below we can execute this code. We can select the modality we want to use. Let's use visual for now. This is fine. And then we can see that it reduced the feature dimension from 8,192 to 250, which was the number of principal components. And it's a drastic reduction. And yeah, you can also do the same with the audio and language modality and see how much they can be reduced. Okay, so now we learned how to extract features from the multimodal stimuli that we have, and now it's time to train and validate an encoding model that takes the stimuli features that we extracted as an input and predicts the fMRI responses that happens when the human subjects watches that chunk the features belong to. So in this section, I will show you how to train an encoding model using season 1 to 6 of the TV show Friends. And as mentioned in the beginning, you can right away start with this section because we will provide all of the PCA downsampled features for all the episodes already. So here this graph shows again the general idea. So we have the movie data, extracted features for all modalities, and using these features, we will train a regression model using the fMRI data that elicited during these scenes. And in testing, we will again use the PCA downsampled features of our validation set, put it into our already trained regression model, which will then return a prediction of the fMRI responses that could have happened while watching that scene. Again, this is how we do it for the sake of this tutorial. Feel free to use whatever more sophisticated method you like. Down here we have some parameters for this section which you can select. First off, you can select which subject data you want to use for training. For now, let's just stick with one. Then you can select the modality on which you want to train your encoding model. You can select any modality, for example, to just train it on the visual data, but you can also select all modalities, which I am doing now. Excluded sample start basically excludes the first number of fMRI samples. And the reason why we implemented this is because of that hemodynamic response delay I mentioned earlier, which results in the earlier fMRI responses containing less information than later ones because the bold responses takes time to build up. And this is why the first fMRI samples will not contain stimulus-related information. And excluded samples end is the same, just excluding the last number of fMRI samples. And reason for that is that the fMRI sometimes ran longer than the stimuli. HRF delay is the same as above, the delay of registering the blood oxygen levels. Stimulus window, this value says how many stimulus features we want to use to model each fMRI sample. So for example, if our current fMRI sample is number 20 and we have a window size of 5, it would use the stimuli chunk 15 up until 20 for the fMRI sample of 20. And if we also add the href delay of, for example, 3, that means we even go 3 stimulus chunks back, because as we learned, fMRI response takes time to happen. So that will be 13 until 17 then. Okay, movies trained, this will be the list of movies and seasons used for training the model, and movies val will be the movie or season we will be validating our model on. And for this case, we will train on season 1 to 5 and the movie 10 dataset, and validate on season 6. Okay, so let's first load up the stimulus. As mentioned before, we provide pre-computed PCA downsampled features for all the modalities. They are all computed in the way we did it in section 2, but to save some time, you can find them in the drive under this path here for each of the modalities. And this code cell below basically just loads them up. We enter the data directory and the modality we chose above, which will then create a feature dictionary with the modality as a key and the features as values. And if the modality is all, we will just have all the keys in the dictionary. And if you print out the keys, you will find subdictionaries with the episode titles as key and the features and the feature arrays. And of course the same here for the movie dataset for all the modalities. Okay, so now we also need to load up our fMRI responses. They are in a known location in the Google Drive. And what happens in this function is that we just load up the fMRI directory, link up the H5 file for friends, and down here also for movie 10. And we also have some additional code here because there has been 2 repeats for the figures and live movie. So for all the splits that we have, or for all of these recordings, we just take the mean by adding them together and dividing them by 2. And that's basically it. And you will see if we print it, we can see the sample dimensions and the 1000 parser dimensions. And just like the feature data, it's organized per movie. Just the feature dimension is different because of the parcels. But that means we basically have the fMRI and the features formatted in the same way. And that means we can start with the encoding model training. And for that, the first step will be to align the fMRI responses with the feature data, because we want to get away from the dictionaries and have the data in the shape of training samples times parcels or times features for the feature samples. So what does this function do? In the parameters, you can already see that here is the place where the exclusion of the beginning and the end fMRI data takes place, and where we apply the stimulus window and the href delay based on the selection we made above. Okay, so let's first create empty data variables for the aligned features and for the fMRI. For the fMRI, we already know the feature dimension, which is 1000 parcels. And now for every movie that is in our dataset, we will first collect the available splits that we have. So in our case, a movie is 1 season of Friends or 1 movie 10 movie, and a movie split is the parts in which each Friends season or a movie is divided in, and each split has its own separate fMRI run. And then we will loop over all the splits that we have for one movie, which in the case of the movie Friends Season 1 will be all the episodes or splits that make up the entire recording of Friends Season 1. And first we will deal with the fMRI data, where we exclude the first and the last chunks as by our selection, and then we append it to our created list above. So right now it's, for example, episode 1 of season 1. And now we will move over all the fMRI samples that we have. And now for all the modalities that we have loaded, we plan to append them to fall. So if our modality is visual or audio, select the chunks that we want. For instance, if we are currently at chunk 20, we might want to include chunk 13 to 17 of the modalities combined for that single sample of fMRI data. So here we look at the chunk number, add the excluded start chunks, subtract the href delay and the stimulus window +1 to get the start index of the chunks we want to include. And the end chunk is just the start index plus the stimulus window. And this will basically leave us with a range of chunks we want to include here. And this if clause above is just in case there are not enough stimulus for the selected window. So it will just take whatever is available before. And same with the end. So if the end index is larger than the available stimulus chunk, just use as last index whichever is the end of the stimuli data, so we do not get out of bounds. But yes, now that we collected a stimulus window for the current modality, append them and flatten it into a big array. So that means for sample 20 of the fMRI data, we now have, for example, the flattened chunk 13 to 17 of the stimulus data. And for chunk 21, it will be chunk 14 to 18 and so on. And for the language modality, it's a bit different since it already spans several samples, so we do not use a sample window here. We just adapt the excluded samples and the href delay, and then the rest is the same. And this will be appended at the end, which will lead to two arrays, the fMRI responses, which are solely just appended across all movies, and the feature representations, which are collected over all the fMRI samples and flattened across the modalities. Okay, let's execute the cell. This might again take a minute or two. You will see that the sample dimension is the same, which is as expected, because these are all the samples across all the movies, and the feature shape is the appended chunks across all modalities. So we chose our modalities, so this number is 1600, but if we had only chosen visual, this dimension would be smaller, I think like 1250 or something. But yes, this is about that, and now we can go to training the encoding model. Okay, so as you have seen, we have now two arrays in the same shape, just with different feature dimensions, and we can plug these directly into a linear regression model. And for that, we can just load up linear regression from sklearn. And this is a very simple model, just for the sake of the tutorial. For the challenge, feel free to use whatever method you like. And we will initiate and train the model here. It's a rather simple method. It might take some time. Sadly, there is no progress bar here, so just wait a short time. Okay, so now that the model training is done, we can now deal with the validation set. And for that, we will again just align the features and the fMRI samples as we did with the training data. Remember that up top we selected season 6 for validation, so we are feeding this movie val variable into that function now. And as you can see again, we have our nice data here. And now we can use the linear regression model that we trained and feed our validation features into it. And that means we will show the model now the PCA downsampled features of season 6, and the model should return predicted brain responses. And as you can see, the predicted brain responses and the actual brain responses have the same shape. Obviously, during the challenge, you will not have the actual brain responses, you will just have to predict brain responses. But we have them for season 6, which allows us to see how accurate we were. Okay. So in this function, we will enter the actual fMRI responses, the fMRI predictions, the subject to grab the correct brain atlas for plotting, and we also enter the modality for labeling reasons. So we first create an empty array in the shape of the brain data voxel, so 1000, and then we will fill this empty array with the Pearson R value between the actual brain data and the predicted brain data to see how much they align. And this Pearson will return a correlation value for each parcel, so we have a fine-grained view of how correlated our prediction is to the actual fMRI data. So that's happening here. And then the mean encoding accuracy is just the mean across all parcels, so we have one value at the end. And then, as before, as in section 1, we will load up the atlas file and plot it onto the brain using the NILearn. And then we can see what the overall mean accuracy is, which is 0.195. And you can see which regions of the brain were more accurately predicted than others. And you can see higher correlations in the visual regions here, especially, but also here. And this is basically what will happen on the CoderBench platform, but instead of testing on season 6, we will test it on season 7, which is withheld. And then you will be informed about your accuracy, including plots like this, on the website. But more about that in the other CoderBench related video. But this makes a nice transition to the final chapter. Prepare the challenge submission. Okay, so in this final section, I will show you how to prepare and format the predictions for the challenge submissions. For this section, we will provide you with the pre-trained encoding models for all subjects on season 1 to 6 and movie 10, but this time using rich regression. We are doing this so you can straight up start with this section without needing to execute the other cells, and because CodaBench requires you to submit the responses to all 4 subjects, and since it will take some time, we provide the data for you. Again, this is a very basic model and training routine and just acts as an example. Okay, I will probably go a bit faster across this section because much of this code is reused from the previous section. So in the cell here, we will load the PCA downsampled features for season 7, just in the same manner as we did before, but directly for all the modalities. And as you can see down below, we have the data in the same form as before, separated across modalities and episode splits. Then, just as before, we are aligning the stimulus features with the fMRI responses. It's basically the same code as before. The only difference is that you will not have the fMRI responses to season 7, which means you don't have the exact number of fMRI samples. And this is also what I mentioned earlier in section 1. This data here will give you the information on how many fMRI samples you will need to predict, since you don't have the test data available to look for yourself. And this is what you can use this file for. And this will be very important for your predictions because your predictions need to have the same shape as the actual fMRI data. Another difference is that in the training we discarded some fMRI samples from the beginning and the end, but we cannot do this here because for the challenge evaluation the fMRI samples must be identical. Otherwise, again, the platform will throw an error. So no discarding of samples for the prediction. However, the scoring program will take care of this because it automatically removes the first and the last 5 fMRI samples, so don't bother too much about that. And since I explained this function above already in detail, I will skip over this one. And since we have all the subjects now, it will create a nested dictionary with subject numbers as first layer keys and the Friends Season 7 episode as second layer keys. We printed out some example for each subject here. And now we will load the encoding models that we provide. This code will basically just iterate through all the subjects that we have, go to the path and load the encoding model that belongs to that subject because we have one encoding model per subject. And then it will load it into an empty ridge regression model and return all models in a dictionary. Okay, so now comes the important part, predicting season 7 responses and bringing them into the right format. So at the end of the day, it's only important that the submission format is correct. And here you can see how the NumPy file is supposed to look like. You want to have a nested dictionary where the first layer is the subject ID, and also make sure to write the IDs correctly. So no subject, but use sub. And then the second layer will be all the episode keys. And here also make sure to have the correct writing of the names. Otherwise the platform will throw an error. And then for each subject and episode, you will have an array of the shape samples times 100. And that's basically it. This cell will initiate that submission dictionary, and then for each subject and episode, it will use the ridge regression model of that very subject to predict the brain responses to that given episode. Again, you will enter the PCA downsampled features of that episode here, and this will return the brain responses in the shape of samples times 1000. We are also applying float 32 to reduce the submission size, which I would encourage you to do as well, because otherwise the file will be twice as large and it might take a bit longer to process the file on CodaBench, and it will also clutter your storage there. And then it will fill the dictionary. Okay, so here the cell again will show you the layout, the first layer being the subject and then all of the episodes with their different shapes, and this is being done for all the subjects. And then finally saving that dictionary in a NumPy file. It will just save it as a NumPy file and then zip it for you, because CodaBench requires the data to be a zipped NumPy file. And after this, you can just download it and submit it to CodaBench. Also, you will see in the CodaBench video, if you submit this file, you will get the exact same results as with the challenge baseline model. Alright, and to download it, you can just go to the location here and download it from your drive. Otherwise, you can just change the path and download it from wherever. But yeah, this has been the video for the development kit of this year's challenge. I hope this information was useful for you. If you want to get more information on how to submit the results to CodaBench, check out the other video, which I will link in the comment section down below. And yeah, I think that's it. Have fun with the challenge and good luck. Bye.